Hello. Good evening, everyone. I hope my slides are visible to you. Start our session. So it's like uh, last lecture, or you can say summary lecture of all over the content that we have covered on this irrigation and drainage course. I welcome you all. I am Karthik Yadav, research scholar in the Department of WRTM IIT Roorkee. So this course is designed by Professor Mailapalli. So he's from Agricultural and Food Engineering Department of IIT Kharagpur. Yes, so this like end of this lecture, and still I want to just give you a quick overview of this entire course. So yes, if you have any query, I request you to write down your queries in this provided email ID. Also, whatever content up to week 12 I have covered or I have summarized them, and also covered certain multiple choice question and numerical question based on that particular week. So all that I've covered in respected weeks and uploaded in this YouTube channel. So either you just scan this QR code or directly click in this YouTube link, and also you can access all the lecture material that I uploaded in this Google Drive folder. So yes, so this is the entire duration, 12-week duration that we have covered, and these are the contents. So today I will basically go step by step and provide you quick overview of each week, and like how we have built upon this irrigation and drainage course. So that will be helpful for you to quickly revise overall content. So in week number one, or it initially we have started with understanding by what is the current land and water availability, because you know that the subject name is irrigation and drainage. So irrigation stands for what amount of extra water we are applying apart from natural rainfall happening in particular area, and that are like directly contributing to the crop yield, desired crop yield, right? And second is drainage. So in first 6 week we have basically focused on irrigation part, and then we have moved towards drainage part, right? So irrigation I already said. So in drainage basically it is like removing of excess water from the crop root zone. So again, either you are removing excess water from surface or subsurface, or you are also reducing salinity, right? Because this problem causes unfavorable condition for plants, right? So in second part of this course, we are focused on drainage design and maintenance and other related aspects. So before we went to the particular problem, we have first understood that what are the availability of the land and water in our planet, and you know that by problems related to the overpopulation, or you just say increasing in population, followed by intensive agricultural practices, growing industries, climate change, seawater inclusion. There are n number of problems, and due to all of this, there is a reducing in water quantity, as well as like there is a degradation of water quality. So that overall causes to reduction in per capita water availability. So this reduction in per capita availability, and still we have a fixed natural resources like air, you can say land, water, right? So water, like per capita availability of these resources is depleting day by day. Due to that, it is very crucial to use these resources very judicially, and for that, like if you are concerning with the like agriculture, so there you have a role of how we can manage these resources, land and water, to get maximum food production. And to understand this concept, we required certain fundamental aspects that is related to soil mechanics, fluid mechanics, then concept related to soil and water. There are certain concepts related to soil and water, or like an entire, if you know hydrologic cycle, so in like in that you know overall, right? So there is like certain watershed if you take. So in that watershed you have different land use classes. You have suppose urban area, then you have agriculture, then you have industries, then you have forest area, and so on, right? And all that required water for sustaining their ecosystem. So, and as far as in this lecture, basically we are talking on agricultural land. As you know that agriculture is like a major uh, consuming sector of water globally, not in India. So it is like in India, it is using around 80 percentage of Indian water resources, and majority of that water resources coming from groundwater. So considering that all, right. Water requirement by agriculture crop, and you know that there is a also water requirement by other sector. And uh, water availability for per capita is depleting day by day. So there is a water scarce condition, water stress condition, depending on water availability. So due to that, we in second part, like you can say parallelly, we need to feed certain population for food, right? So that required growing of food in agriculture land. But still, if you have a limited water, then how you will manage? So for that, you required sustainable water resource management technique, right? For agriculture. So to understand or to develop this kind of technique, first you need to understand certain fundamental principles. So we have started with that, and that we have in detail we have talked about soil water properties. So like what kind of physical properties that are governing the water flow. So it's like soil texture, soil structure, you can say particle density, dry bulk density, or wet bulk density. Then you have a porosity. So among all these, like major factor is porosity. You can say soil texture, so that governs the water flow. And we also understood like how we can calculate each one of them. Then you have what type of soil water you have, and what kind of factors affecting the energy level of soil. So in terms of types of soil water, so you have like different kind of water like gravitational water. So it's like drained by gravity. Then you have a water that is tightly bound to the soil. You have a loosely bound just hold, so that it's field capacity water, right? So there are different aspects. I'm not going that into detail, I'm just providing you overview. So then we also move to like what are the constants. So it's again like field capacity, point melting point, ultimate melting point, like available water. So there are different terms that help us to design the irrigation technique, or just choose like which kind of irrigation technique is best suitable. So next to that, we have focused on like to introduce the irrigation, as we understood that there is a problem in like overall water sustainable water management, because there is also higher loss of water during, like if you are doing irrigation with conventional irrigation techniques like furrow irrigation, basin irrigation, check basin irrigation, that have certain advantages and certain disadvantages. So in that case, understanding this concept is a very crucial. And let's continue. So I already discussed about this irrigation and drainage aspects, why it is different. Then let's come to the irrigation. So irrigation, main concern in irrigation is like how much to apply of water, how to apply, how much to apply, and when to apply. So how to apply? So in that your terms comes like apply. So how to apply in that you have to understand which kind of techniques available, what are the modernization or things you can do. So all these things come under this how. Then how much to apply. So in that's totally depend on what kind of soil you have, what kind of plant you are growing or crops you are growing there. Then what are the hydrogeological parameters that decide this, how much of water we need to apply and when to apply. Again, this are like interlinked, like depending on the crop type. They have certain crop growth stage. They again they have a different kind of irrigation interval. So all that we have looked over it. So this will help us to decide when to apply irrigation. So at the end of this week one, just like this concept, we found that to understand the irrigation and drainage principle is a fundamental outcome at the end of this 12-week course. Then we have also talked about design of gravity and pressurized irrigation system. Then we have also focused on understanding of ground hydraulics. Fourth one, like we have also focused on design of surface and subsurface drainage system. Then we have or like uh, quickly check or like just go through certain famous irrigation and drainage models. And then finally, like we have also talked about economics aspects of irrigation and drainage project and its efficiencies. So overall, in like in terms of net shown area in overall in India, so it's like 141 million hectare of land. So that is like so for your uh, info. So we right now we have a total 329 million hectare of land, and out of like 43% of land is like doing agriculture. So it's like net showing area. So it is 141 million hectare. Then in terms of irrigated area, so it is like only just 87.23 million hectares. So it's like more than, it's just like just less than or not less than, it's far greater than, far little just greater than 50% of the net zone area, right? So there is still huge gap in net zone area and irrigated area, right? So this gap is we just need to fill out by using certain precise irrigation technique, right? So this technique is very crucial because if you do not doing this the right time, right way, that will lead to unsustainable development. And if you see this productivity in this both kind of area, irrigated and rain-fed area, so there is a huge difference again, because in rain-fed area you are just not doing any extra irrigation part. So you are not feeding. plants or crops at the right time, so that ultimately causing reduction in yield. If you anyhow introduce this irrigation in this rainfed area also, so that will help us to increase your food production, and again like helping us to feeding the population. And then in irrigation we have also like in detail uh, focus on benefits of irrigation, its advantages, disadvantages. Then certain irrigation terminology like intensity of irrigation, waterlogged area, field capacity, probability, wilting point, base period, delta, duty. So that all help us to design efficient and effective drainage irrigation system. And these are the just fundamental aspects of soil water availability to the plant. So there are different kind of water. So like gravitational water, capillary water, and hygroscopic water. Right. So there are different kind of soil water availability plant that we have look over it, because this ultimately designed like based on your soil type. This help us to understand, okay, what kind of, if we are irrigating certain soils, what amount of water is available, right, for crops. So understanding this concept is very fundamental. So for that, like we have just decided, or you just simply understand that if we are flooding any soil, so it's not like that all water will retain in soil or it's moving. So soil absorb the water, but it have certain capacity. So whatever capacity it have, and beyond that, whatever water will move down. So that is your that is the water that is come under gravitational water. So it is just moved by gravity. And after gravity drainage, still there is some water that let uh, adsorb on soil surface, right? Because it attracts this water, but it have a limited capacity. You can see this is just having certain radius only, depending on what kind of charges you have on the soil and what kind of organic matter you have. And it's like more chemistry part. So this just thing you need to understand that uh, different soil have a different field capacity. So field capacity is just meaning that it is the capacity of storing water against gravity. Okay. So this help us. So this is just maximum water availability. Okay, for a plant, because they stay for a certain period and it's not just not go away in the drainage. And also it have a condition like aeration, sufficient aeration, so plant also can take oxygen. And then you have a hygroscopic water. So this hygroscopic water is like at a permanent melting point, so it is tightly or just like tightly hold water on the surface particle. So, and in this condition, like if you have like a plant and your soil have a hygroscopic condition, so what will happen in that case? So there is always trade-offs. So plants say that okay, I want water, then soil say okay, I also want some water. So like in this that trade-off, what will happen? Like this adsorption capacity of the soil is more or like far greater than this plant extraction rate. So in that case, plant won't able to extract this water, and if plant will not get water, that ultimately gonna die. Okay, so each of this condition have a certain pressure. So like in gravitational water, it's just like 0 bar to one third bar. Then in a field at a field capacity, you have in between one third to uh, one third to 15 bar. So it's like not a field capacity, sorry, so it's field capacity of one third to 115 bar. Okay, it's like minus. And at capillary water, so capillary water is just part of you can say also like available water. So that lies between one third to 15 bar, and that is water not available to plants, so that is come under 15 to 31 bar. Okay, whatever water that is uh, drop very tightly on the soil particles, that is above greater than 13 bar, and that cannot easily extract by a normal condition. So that is this called hygroscopic water. Then we also focused on like soil moisture, because just all this have a look at over it, like this is representing saturation condition, this representing not fully saturation, but like you have a maximum water content that soil can uh, take against gravity with certain air porous space. And in this case, you like tightly hold water and much less water. So all of them have different soil moisture content. So we have also looked over it. So how soil moisture we is defined. So it is just like amount of water present in soil. So there are different kind of metrics or different kind of methods that we are using for soil moisture measurement. So there are different methods, and certain are direct, certain are indirect. So currently, this direct methods are in this we are just doing taking some soil sample, doing its heating, doing some chemical reaction, and identifying whatever amount of water present in the soil. While in indirect case, we are using certain sensors or certain soil physics techniques, so that will help us to identify indirectly soil moisture content. Then nowadays there is also growing interest in remote sensing of soil moisture. So in that also we have quickly look over it. And then after soil moisture, so second part come is other understanding other hydrological factors that impact the water availability of the plant. So let me provide quick overview. So if you have plant here, if you have soil here, okay. So the soil have a different water holding capacity and plant required water, right? So suppose you have soil here and you have a different water here, like in a yellow, just so what will happen now? So there are two situations. If you are growing crop in a kharif season, so there you have a rainfall, sufficient rainfall, so it is occurring certain frequency, so it's still it is random. But nowadays there is a techniques that are like just predicting rainfall and telling farmers when to irrigate, right? So suppose you have a soil moisture, but in during non-monsoon season, what will happen? This whatever soil moisture is present, if you'll grow certain plant or crop, so this slowly will reduce. Okay, this water will get reduced. So in that case, we need to apply water, right? Again to soil, and this soil pores gets filled and plant will take water. But this just in a simple word. And now if you want to understand, okay, what is water requirement of plant? For that purpose, there is a concept called evapotranspiration that comes into the picture. So that technically defined, okay, this is the water requirement by any crop. Okay, and that totally depends on what kind of crop growth stage that particular crop have, and what are its water requirement. Suppose rice sugar can have a high water requirement, while certain pulses or wheat you can say that have a lower water requirement. So Considering all this situation, we have understood like uh, evapotranspiration is a major water requirement by plant. It is just combination of evapotranspiration from soil and transpiration from plant leaves. And by measuring this with certain instrument that will help us to decide entire irrigation scheme, or which kind of like in the scheme also, what are the irrigation interval, and so that basically tells about irrigation scheduling. So again, in this also you have a direct method, indirect method. So I'm not going into the details of it. So just for your quick overview, and next to that, we have a different approaches like for crop coefficient, because crop coefficient is the approach that we are using to from if you want to, if you want crop evapotranspiration. So what you are doing, you are just multiplying reference evapotranspiration with crop coefficient. So crop coefficient, there are two types, so single crop coefficient and dual crop coefficient. In case of single crop coefficient, that may not accurately reflect the varying water needs in the different growth stage, so it is less precise in the regions with significant climatic variation. A dual crop coefficient approach, so it is a more complex and data intensive compared to the single coefficient approach, and it requires detailed field and continuous monitoring data. So this is irrigation scheduling criteria, right? So that is first based on the soil water regime. So soil water regime means soil moisture content. Based on soil moisture content, by deciding just like with the feel and appearance, you decide okay, now water is not enough for plant. You just irrigate. Then you just check the depletion of available soil moisture with certain instruments or certain direct indirect methods that we have looked over it. Then you have a climatological approach. So in that, again, you have different methods that are widely used. And finally, plant-based indices. So plant-based indices like just measuring plant water potential, plant temperature. You just say visual symptoms by looking at its color, its appearance. So that all helps to decides the when to irrigate. Okay, but this techniques required lots of uh, like lots of field work. So it's not like in one day you will get all this. This required too much of field work. Then these are the different methods for estimation or measure modeling of evapotranspiration. So certain are based on temperature, certain are based on radiation, and certain are based on evaporation. And also there is certain methods that are combined of all these factors. And finally, we have talked about crop water requirement and irrigation water requirement. So I understood this concept is also like important because crop water requirement only talks about at the field level, right? While irrigation water requirement that talks about entire area where you need to provide irrigation. So that also includes various losses that is happening while transferring some water from one place to another place. So that like water losses from evaporation through irrigation network, water losses from seepage, lateral flows, and so on. Okay. So now it's just already I've discussed, right, when to irrigate based on which condition. Then we have moved to week number three, where so once we have decided, okay, these are the water requirement by understanding evapotranspiration. So this is a crop water requirement for that particular crop, and then now if you want to transfer this water to any field, right? So you required certain water conveyance structure. So there are various structure, conveyance structure, diverse structure, and also uh, majorly that have different uh, concepts. So we have not gone in that detail, but we have understood this, and then we have moved to open channel flow to irrigation. So open channel just again like which kind of channel we required. So it's have a certain shape. So here, for example, you have a trapezoidal channel, then maybe you have a semicircular shape, You have a rectangular channel, triangular channel. So different channel aspects you have, but depending on your field condition and economic status of any project, you require the what you require to design this. And like main parameters that we are look over during open channel design are top width, bottom width, freeboard, side slope, and with perimeter, hydraulic gradient. So these are all important to get the design discharge. And then we have talked about hydraulic and energy grade line for pipe. So this is also famous. So in like for pipe flow, for like open channel flow, this energy line and hydraulic gradient line are both are at equal position, while in pipe flow this energy line is located above the hydraulic gradient. And all this like types of flow in a pipe that is defined by Reynolds number. So it is just rho d by mu. So it is like viscous number two. Uh, sorry, yeah. So it is like Re, and Re is just uh, it is like ratio of inertia force to viscous force, right? And next to that, Reynolds number classification, that also we have look over it for pipe flow and open channel flow. So like for pipe flow, if RA is less than 2100, so it means it is flow is laminar. But in case of open channel, if it is less than 500, uh, then your flow is laminar. Then in case of pipe flow, if your flow is transient, it means Reynolds number is between 2100 to 4 uh, 2100 to 4000. And if it is greater than 4000, it means it is turbulent flow. While in case of open channel, it is like 500, less than 500, 500 to 10, 500 to 1000, and greater than 1000. Then we have also focused on canal irrigation scheduling. So that's again not going into the detail. Then we have also focused on basic terminology and hydraulic principle of flow measurement. So flow rate or discharge, so the quantity, so it is just quantity of water flowing per second through a channel or pipe. Then velocity, so it is like water approaches, reaches, flow meaning advice. So it is we can just simply also calculate it by certain approaches, so that we have looked over it. So area velocity method, or you just use current meter method. So there are different aspects. Then continuity equation, that's also like a fundamental equation and most widely used in hydrology. Then you have Pascal law. So again, like it said that a fluid at a rest or in a motion that exert pressure on its surface, and in the static fluid, intensity of pressure at point is equal in all direction. Then already like different kind of methods you have, but broadly it is classified in the three terms like volumetric method, area velocity method, and pressure method. So in volumetric method, we are just measuring by the bucket, certain structure like notches, weirs, plumes, centimeter, while velocity area methods, in that area and velocity you need to measure separately. And for velocity measurement, there are certain devices like current meter, pitot tube, float, etc. And then you have a tracer method, dilution method. So you are injecting certain non-reactive chemicals that are not harmful to ecosystem, and then just tracking their travel time from one place to another place. You are measuring the velocity, and ultimately your aim is to get a discharge. Then we have also talked about basic terminology in hydraulic principle of flow measurement. So in that we have talked about specific energy and critical depth. So that will help us to design various structures at the end of your channel where you are carrying the water. So very important to understand all these aspects to design the conveyance structure uh, or for the irrigation, right? Conversion or diversion structure. Then we have looked over it, various kind of meter that are we are just fitting in the pipe or just like majorly in a pipe. So you have trajectory meter, orifice meter, partial flume. So it's like open channel structure. So that have a different aspects. But main things to remember here is the design of partial flume is happening based on throat width. In that also you have a different aspect like cutthroat partial flume. So that is like a most economical one. But depending on field condition and uh, price or like economics budget you have, you decide which kind of uh, meter or flume unit you can use. Okay. Then uh, so yeah, if you have any question in between, just ask me. Okay, just stop me anywhere so we can discuss because this is just last lecture and I'm happy to answer this if you have any query. Okay. So yeah, if you do not have, just finish my part and in between time or during a break, you can write down into the chat box or we'll just discuss it. Okay. So in week number 4, so we have started talking about till week number 3 we have fundamental aspects of soil and water movement in any farm and if you want to carry your water design water from one place to another place you need certain irrigation infrastructure. So that infrastructure also have a different kind of meters, flow meters, so you just regulate everything. So till now we have covered that, and now in week number 4, like we have more focused on irrigation aspects. Okay, so irrigation methods generally divides by three border aspects. So first one is based on energy or pressure required. So based on that, you have a gravity irrigation or pressurized irrigation. So gravity irrigation like border basin and furrow irrigation. So it is generally have a low cost and it's simple in operation. While pressurized irrigation, so drip and sprinkler irrigation system, so it is a precise water application and have a better efficiency. Second one is based on placement of irrigation of water. So in that you have a three categories. So first one is surface irrigation, subsurface irrigation, and third one is overhead irrigation. Surface irrigation again have a border, basin, furrow, and drip irrigation. While subsurface irrigation, you have a subsurface drip irrigation system or any other methods. Then in overhead irrigation, you have a sprinkler irrigation and hand watering. And third one is based on weighted area of crop root zone by irrigation. So in that case, you have flood irrigation, drip irrigation, and sprinkler irrigation. So starting of this lecture or initially we have focused on surface irrigation methods and most common furrow, basin, and border irrigations. Each one of them were different criteria and which kind of crop you have. So furrow irrigation is like accomplished by running of water in a small land. So it's like furrow created here in between your valley. So your ridge, so you're just allowing water to move in this valley kind of space. So however, this kind of length of furrow, width of furrow, and like what kind of grade you have to apply, all depends on what kind of soil you have. And in general, like soil, loam soil with a mild slope that have around 0.2 0.5 to 2%. and labor is required is quite high in each one of the surface irrigation system. And like major initial cost or investment cost in this is just construction of. Then second one is a basin. So basin irrigation is in that field is divided into the small units surrounding by levees. So this is just levees. You have a surrounding basin. Again, you have constructed levees here. So this is levee for area irrigation conveys and or diversion structure. But in general, basin size is in between 1 to 15 hectare, and its length is around basin length is around 100 to 400 meter long. And it is commonly like practiced for rice and orchard tree crops. So in that also you have a different kind of basin. So one is a level basin, second is a graded basin. So level basin, so water is held until infiltrates or is drained away minimum runoff losses and higher application efficiency possible. While in graded basin, so it is like contour levee irrigation. So it is constructed with two levees parallel and two perpendicular to the field contours, and water enters along the upper contour and flows to the lower. Then we have also focused on sprinkler irrigation system. So we know that water is in the sprinkler one irrigation. Water is delivered through pressurized pipe network to sprinkler nozzle jets, which spray the water into the air and fall into the soil as an artificial rain. So again, it have a certain criteria like light sandy soils are well suited, because you know that if you're doing irrigation it flood in this kind of soil, so all the water will quickly drain out and your water losses is higher. But if you have a sprinkler irrigation system, so it is like more like rain rain happened. So in but in this case, if, since it is a pressurized irrigation system, so your water application amount is much lower than the surface irrigation method, and it can be used in any topography and sometimes used to generate the seed and established ground crops like lettuce, alfalfa, and so. They have a very high efficiency as compared to other surface irrigation method. Then we have also looked over it, drip irrigation method. So it is like a constant steady flow water applied directly to the root zone by plants by means of application of operated under low pressure. And its applicators are like orifice emitters, porous tubing, and perforated pipe. And it is like most widely suited for high density orchard tree crops and high valuable horticulture crops. It's not designed for large root systems. It suited for situation where water supply is limited. But still, there is a research going on in this aspect also. So the aim of surface irrigation system design that we have looked over it is to identify appropriate inflow rates and cutoff time. So maximum or desired performance is obtained for a given field condition. Now you also have a different kind of phases during irrigation, so that you need to understand if you want to design an irrigation system. So advanced stage, storage phase, depletion phase, and recession phase, so these are the fundamental. So advanced phase is just begins when we start water application into the field and ends when water reaches to the downstream at the end of the field. Then you have a storage phase. So storage phase begins when water advances phase ends. It means once it reaches the end of the downstream, and storage phase ends when inflow ends. So whatever water we have, whatever time we have provided from starting of the water flow to the stopping of water flow, that is your storage phase. Then you have a recession curve or depletion phase. So it begins when storage phase ends and when inflow ends. So ends when depth of flow at the headband becomes zero. Then you have recession phase. So it begins when depletion phase ends and continues until drying front reaches at end. It's just figure of just this conceptual understanding, and each irrigation system have a different kind of phases involvement. that decides how uniform when water will reach it, and uh, depending on what kind of length you have, width you have, slope you have, everything okay. Then we have also looked over at the Saint Laurent equation. So it is like a mathematical foundation for describing this water movement in open channels and surface irrigation fields. So like this model have a different condition, like full hydrodynamic model, zero inertia model, kinetic wave model, volume based model, and each of them have a certain governing principle, key simplification, and field example where we can use this kind of model. Then this I've already like talked like about furrow irrigation, pod irrigation, and check base or basin irrigation in general, and where we can use it. And then from next week, week number 5, we have focused on pressurized irrigation system, where you have a drip irrigation system and sprinkler irrigation system. So low pressure irrigation system, like for drip irrigation, where your pressure is around 1 kg per centimeter square, and its application rate is around 1.25 to 5 centimeter per hour. While in the case of sprinkler, your pressure is around quite high as compared to drip irrigation system, where you have a 2 to 4 kg per centimeter square, and the infiltration rate is around 4 mm per hour. And you have here a riser, so which riser is having a rotation from 90 degree to 60 degree, and generally like types of first we have started with the types of sprinkler irrigation system. So sprinkler irrigation system, it's like have a portable system, semi-portable system, site move or portable irrigation system, and continuous move system. So portable system, it has a portable main lines and sub mains, laterals, and portable pumping unit, right? While semi-portable system, so it is similar to portable system except the location of water source and pumping plant is fixed. So in portable system, everything is portable, while semi-portable, majority of things like main lines, sub-main laterals that are movable, while other like major like water source and pumping plant. So it's like filtration and everything. It is fixed. The set move or portable system, so it is movable from one set of position to another by hand or mechanically, and the new continuous move system. So again, by from name itself, it's telling it has a laterals and circular that are remain connected to mainline and move continuously as water is supplied. So these are just types of sprinkler irrigation system and its detailed names. And then we have talked about components of sprinkler irrigation system with description of essential finding and necessary. So in continue with this, we have also focused on drip irrigation system. So drip irrigation system is having two main aspects. So that is your control head and distribution network. So control head is this includes pump, overhead tank, fertilizer or chemical application device, and filters. So this is your control head, right? Where you have everything like filtration system, fertilization system, then you have a pump, and then once you divert water to the field, there you have a distribution network. There you have a main, sub-main, laterals, etc. And on that you have valves, different kind of valves. So perform then by defining everything in this drip irrigation system briefly, we have focused on performance evaluation of the drip emitters, because ensuring uniform uniform water movement is mandatory to get desired output from entire field and increasing be- uh, increasing benefits over the whatever cost we have put it. For that purpose, it is very crucial. And in that, you have different characteristics like manufacturing characteristics, operational characteristics, and hydraulic characteristics. So manufacturing characteristics, in that you have coefficient of variation from manufacturer, that measure that is around just 1 kg per centimeter square. And operational characteristics, so it is uniformity of water application through gravimeters. And hydraulic characteristics, so that defines your shape of emitters. Okay, that's just you can see design of emitters. And installation of drip irrigation system, again you have different aspects. So first you have to install head control unit, in that you have filters, pumps and fertigation equipment. And distribution network, your installation of main sub-main lines, laying laterals, uh, punching laterals and fixing emitters. Then operation of drip system. So in operation, you have a certain aspects. So like operation, just like you need to ensure it carries design discharge, and you install it right place. Then obviously you have a maintenance part, so you have to maintain each filtration system depending on its nature of removal of particles. So filter cleaning is a heart of drip system, and its failure will lead to the clogging of entire system, and you just having no water at the end. That's why it is very important to maintain it frequently or regularly by following mandatory guidelines. Then you have also need to maintain a fertigation system, as like the Venturi injector should be operated with clean water for 10 to 15 minutes to prevent clogging. And maintenance of main and sub-main pipes. So in that you have a different kind of valves to escape the silt, removing end caps from laterals. Then you have to do chemical treatment for removal of clogging and purging. And finally, maintenance of lateral pipes and dry perimeters. So that I'm not going into detail. So just quickly recapping, as we have also limited time. Then in week number 6, we have focused on groundwater hydraulics, because whatever water we are putting as irrigation, it's not like all are just used by plants. Certain water is going down and doing some recharge, certain water is moving horizontally or laterally, that ultimately also leading to uh, contributing to interflow or base flow. So, to understand the groundwater hydraulics part, so first we understood the soil water zone. So it is just soil is just beneath the surface, and there exists large fresh water. So four zones we can define. So first, like is the soil moisture, then you have Widow's zone, are also called unsaturated zone, then you have groundwater and deep lying groundwater. Okay. And in general, like whatever material we have beneath the surface, it just categorized in four major parts. So first is aquifer, then you have aquifuge, you have aquiclude, and aquitard. Aquifer, among all this, aquifer is the geological formation that yield a significant quantity of water, right? And that defined as aquifer. And most common example of aquifer is sand, gravel. Then you have aquefuge. So there is fuge, it means there is a no interconnected pores, it means there is a no water. In aquiclude, so it is like clay kind of structure. So you know that clay kind of structure that store very low amount of water as compared to other part, uh, right? And like also there is a problem related to water transfer from one place to another. The aquitard, so it is geological formation whose hydraulic conductivity is just too small to permit and development of well or spring, but sufficiently large to influence the hydraulic of aquifer adjacent. Then we have also talked about different kind of springs like contact spring, depression spring, artesian, and tabular spring, and each one of them are different kind of features. Then we have talked about aquifer properties, so that basically transport water from one place, transport, store water, and at yield at the right time. So for that, you need to understand again like certain principles like porosity, permeability, hydraulic conductivity. All this help us to decide which kind of aquifer we have and how it will store water and release the water. Then we've also decided, or just quickly go through the steady state flow in wells and confined aquifer and unconfined aquifer, and that ultimately help us to design the extraction rate of the any location or like where you have a well. So that we have discussed, and also we have more discussed on like its assumption in steady state condition, unsteady state condition, as well as what kind of losses that is happening during uh, this kind of event. Okay, charge event or like just calculation. So that already we have discussed in detail during week number 6. Yes, in week number 6. So before we start with week number 7, let's have a quick break here. And if you have any query, just write down the email ID, just chat box, or you can just directly ask during after small break. Uh, Friend, let's finish our remaining part. So it's like more fresh content, right? So in like from week number 7, still we have focused on pumping devices, like as water requirement major is fulfilled by groundwater. We need to understand, or like if you want to transfer water from one place from the place, you require certain lifting devices. So lifting device is generally classified as low head water lift, medium head water lift, and high head water lift. So it's like based on what are the lifting head, suction head. So it is like height of lift is less than 1.2 meter. It is come under low head water lift. If it is in between 1.2 to 10 meter, then it is come under medium head water lift, and if it is greater than 10 meter, then it comes under higher head water lift. Now, you have certain indigenous water lifts and you have a pumping device. So, indigenous water lifts are like manually operated, animal operated, and certain power operated. So, in power also you have electric power, solar power. You have certain mechanical power. So, all that have a different principles of operation, and but among all these, like pumping devices are nowadays most common in most of region, but still certain indigenous water lift devices are still in use in certain hilly regions where you not much electricity available, and like power operation are possible. So there still this kind of structure are available. And in pumping, basically you have positive displacement pump and variable displacement pump. So positive displacement pump are generally uh, having a same discharge for it's like you just say that heat discharge like pressure discharge should be the constant. While in a variable displacement pump, you have a different kind of pump where your head and discharge relationship having an inverse relationship. So here you have head discharge relationship, it's a constant. Here you have a very like inverse relationship. Okay, and in this there were different kind of pumps, but in variable displacement pump, centrifugal pump is the most common one and widely used pump in irrigation sector. And this again contained that how you can differentiate a reciprocating pump and rotary pump. So reciprocating pump is just that part of a positive displacement pump, and rotary pump is also part of this uh, positive displacement pump. And each one of them have different flow type, pressure, flow rate, maintenance aspect, efficiency, and application. And again, like in rotary pump, you have different pump, like gear and screw, and reciprocating pump have different kind of pump. So I'm not going into the detail. Then variable displacement pump. So it we know that it can change volume or fluid by displacement per cycle, altering the geometry of the pump uh, displacement chamber. And then a specific speed is just index that frequently used in operation characteristics of any pump. So it's just a relationship between speed, discharge, and head. And specific head is speed is given by ns is equal to n under root q divided by h raised to 3 by 4. And it is a dimensionless number that tell us the speed at which geometrically similar impeller would produce one unit of flow and unit of head. And if your specific speed is less than 500, then it is called low. If it is 500 to 1000, it is medium, and greater than 1000, then it is high. Then affinity law you have, so it is also widely used in the design aspects of any pump. So it's just relationship between a total dynamic head, discharge, and brake horsepower of a pump that are relation with size, width, speed, and diameter of impeller. And then in week number 8, we have focused on water quality aspects of the uh, irrigation water. So we know that like irrigation water having a different water quality, like physical, biological, and chemical parameters. So each we need to focus like before we supply this water to the plant. So irrigation water quality is just characteristic of water that will influence the suitability of irrigation, and the poor water quality badly affect the soil structure, crop yield, and long-term sustainability of agricultural practices. So suspended loads greater than 5,000 microbes removed with the filter, while less than 50 to 100 microns require flushing. Okay, so it's always remember or needs to remember that if you have a suspended loads greater than or less than 50 to 1000, then you can just do it by flushing. But if it is more than that, then you need to remove that with filter. Then you have dissolved material, so it is just dissolving of multiple ions, usually phosphates, just in general you can say salinity. Then we have understood the different aspects like water quality indicators like salinity, sodicity. So salinity is just concentration of soluble salts in water, while sodicity is related to the sodium. It is a concentration of sodium related to the other cations like calcium and magnesium. This both affect soil structure because it's like heavily built on the salt, and that just remove or just reduce the available space for water. It also develop cracks so that create the preferential flow pathways. So this is just creating more complex situation as compared to normal. Then we have also talked about other aspects like soil acidity. Then how what are the methods of soil acidity reduction? What are the causes that generally have increased the soil acidity? So that there are certain natural causes, some certain are man-made. So most of them are just like in increasing soil acidity, and it's very important to reduce the soil acidity, because that is if you have higher soil acidity, that cause the bad impact on any crop. Then you have a salinity and alkalinity, so that like factors that affecting crop productivity, soil fertility, and water availability. So this problem are due to the natural and anthropogenic process that I have already defined. And again, that causes of alkalinity and salinity have a natural or anthropogenic. And generally you just decide like which kind of soil it have. So it's just a class of soil affected soil, so it have a different structure, pH, ec, esp, that is exchangeable sodium percentage, and sar, that is sodium adsorption ratio criteria. And depending on that, you decide which kind of soil it is, and that will help us to remediate it quickly and creating favorable condition for plant growth. Then in week number 8, so basically we are focused on agriculture drainage. So drainage aspects we have discussed in more detail. So I'm not going into detail why drainage is required, what kind of challenges, what kind of benefits we have. Uh, just we have broadly classified them in a surface drainage and subsurface drainage. So surface drainage have a different purpose to remove excess water from surface where it is coming from a rainfall. Surface drainage, so where you have a higher groundwater level, then you have a salinity issue. There you are installing subsurface drainage, and each have a different kind of structure, and among that that have a use depending on their condition. And then we have also talked about drain pipe. So drain pipe is having a different material, and among that, like nowadays plastic are most common. Then you have surrounding drain pipe, you have envelope, or just you can say what kind of filter material you need to put. And choice between singular and composite system, so this is the type of drainage system. So that totally depends on your aim, but like composite system are more useful as compared to singular system, and it have a more combination of things. Then we also talked about entry losses and selection criteria of drain pipes depending on our situation. Then in week number 9, uh, we have focused on uh, different kind of systems structure that required in drainage system, like outlet, junction, inlet, and bedding system. Its construction of trenches and trenchless require careful alignment machinery. So if you are constructing tile drainage or mold drainage, so that aspect we have covered, and backfilling and maintenance aspects that also are important. So these are just fundamental concepts related to the groundwater flow that is important when you are designing a drainage system, subsurface drainage system. So for that, this understanding is like a very fundamental. So we use this and derive the drain spacing formula for steady state condition. So this final formula is like L is equal to 4 kdh plus 4 kh square by q. This all are in under root. And in week number 10, basically, our main focus is on the drainage design principle. So there, like key consideration in designing any drainage system is like just getting knowledge of type of drainage system we require, soil characteristics of the field, topography we need to check, hydrological aspect like what are the rainfall, irrigation intensity, and groundwater fluctuation, and what kind of crops we are growing, because whatever situation like waterlogging situation will happen due to poor drainage, so that will causes the uh, poor condition for crop growth and impact its crop health. Then environmental and economical aspects, that is obvious that like major factor and crucial to understand. So the key insights from this is like there are various kind of steady and steady state condition, so that require like proper spacing, sustainable crop yield, and minimize crop drainage costs. Uh, by understanding these aspects of a drainage design and drainage design requirements, so we need to understand drainage coefficients. Drainage coefficient is the rate of water removal usually in a one day, and like so you can say like m of water you need to remove per day, and its method of estimation are different. So this listed here, and like for identifying drain spacing, drain length, and drain diameter, everything we are generally using a Hogarth equation, and that have a certain assumption. I'm not going that in detail as we have limited time. But yes, depending on condition, you have different formulas, and for steady state condition, Hogarth is the most commonly used equation, while unsteady state condition you have a lower term formula de-Hellinga equations where you have water fluctuation, sudden change in a water table after like a recharge event. So this all like considering that, and in week number 11, we have continue our session with the subsurface design part 2, where we have focused on estimation of runoff using various empirical formulas like rational method, SCSN cover number method, Cook's method, and uh, other field methods. So that will help us to decide the design discharge, and once we have a design discharge, then we select the grade. So it is like longitudinal slope depending on the soil type, topography we have, and that will also help us to decide permissible velocity. So in general, like rule of thumb, so like for clay soil it is like zero point 0.6 to zero point 0.9 meter per second, because it have a resistive power, so you can go with high velocity, where for clay soil and sandy soil it is quite lower as compared to that. So in general, sandy soil you have velocities of around zero point 0.3 to 0.45 meter per second. So key idea is select the slope so velocity stay in within this permissible limit. So there is less erosion happen, and less impact on drainage infrastructure. Okay. Now the third part come once you have a velocity decided, you need to choose a cross section of a ditch. So for that, you just use the Manning's equation. So here you identified, here you have a slope, here you have a permissible velocity. So you identified uh, hydraulic radius. So that will help us. So it's just trial and error method. Then you have a continuity equation. So together Manning equation and continuity equation are used to solve the B and D, right? So your B is the bed bottom width, then D is the depth of your channel. So this will help us to design this drainage. Then you have a spoil bank. So spoil banks is just excavated from ditches opposite along to the sides of spoil banks. So its function are provide strength to the ditch embankments, prevent immediate flow of water and sediment back. Then hydrologic design aspects and hydraulic design aspects. So that two are different. So we will look over it in this lecture. And in continuing this, we have also talked on different kind of non-conventional drainage systems. So that is your bio drainage, vertical drainage, and each one of them have a different benefits. So for example, vertical drainage, there you have a deep water control, like around from 20 to 30 meter below the groundwater level using tube well pumping. While in case of conventional drainage, you have a water removal only from 1 or 2 meter below the groundwater surface, depending on installation of this, right? Then bio drainage, so there you are growing certain crops like eucalyptus. There this kind of crops having a higher root zone depth and higher absorption capacity, so it's just taking water for its transpiration requirements, so that will help us to do the proper drainage. Then we have also talked about mold drainage, so it is also part of a non-conventional drainage system. So it again have a certain criteria where it is suitable. So it is like more than 35% of clay, less than 30% of sand. Then where you will land moderate slope of around 0.4 to 4%, and ideally if it is it should be around 3%. Then you can easily construct this kind of mold drainage system. And these are the different criteria, like what are the depth. So depth of mold drainage should be around 40 to 50 centimeter, and spacing of between two mold drainage is 2 to 5 meter, and its maximum length can be go up to 200 meter. And speed of mole plow or having that instrument is should be around 2 to 3 kilometer per hour during installation. That is critical, and that this kind of drainage system are very useful in short term waterlogged field, but it is not suitable for sandy and light soil, because it not sustained, it get collapse. Okay, then these are again like economic aspects, so these are just fresh one, and like I'm not going into the detail as I've already covered this part in the last weeks, and like we have a limited time, and yeah, if you have any query from this slides or these topics, you just quickly ask me, so we can discuss instead of just I'm going again into this concept. So that will be more beneficial. So yes, if you have any query, just quickly ask so we can take few questions. Otherwise, just I will request you to write down to the provided email ID. Yes, so mm, let's wait, or just let me close this session here, and I request you to write down your queries and any inputs to improve this content, whatever I delivered. Just mention that in a feedback form. So I highly appreciate it. So finally, we concluded this session, right? Uh, and we have covered entire subject of irrigation and drainage. So if you have any query, not even right now, just in future also, just write down in this email ID and access all the lecture materials through this YouTube and Google Drive folder. And I wish you a best of luck, and write down your NPTEL examination uh, uh, very effective manner, and I hope these sessions are really beneficial for you. Thank you for joining all the sessions and providing your valuable feedbacks. I hope you will provide for this session also, and yeah, you enjoyed this entire course. So with this, I'm ending this session here. Bye bye.